Okay, we're back. Apologies for the technical difficulties. We are going to fix this. So give me just a moment. I'm going to delete the old stream and let everybody know. So what happened was I clicked start the stream. And it didn't look like it took. So I clicked it again, which immediately ended the broadcast, which was major failure. Okay, so I need to get the new stream shared with everybody. And then hopefully some of you will... Hey, Chris. Thank you for joining. I don't know. It's really frustrating to have that happen. But we're not going to take too long to fix this, so let's give the updated stream link. Okay. And that was annoying. How's everybody doing today? I am feeling pretty good, caffeinated. I'm pretty excited about what we're doing today. You know, as always with these things, I haven't done this particular thing before, so I'm kind of nervous. I'm also excited. It's a domain I really love, compilers. So, and I've done pieces of this sort of stuff before. So we will get we'll get going. It's good to get your exercise doing Pokemon Go. Did that have like a revival or something? I thought I heard something about that. Like they were updating it, or because that was what, a good 4 years ago that it was super hot. Anyway, good luck catching Pokemon. Okay, so last week we got started on building a compiler based on this book, Essentials of Compilation. Oh, 2016, it was that long ago? Holy cow. Okay. Anyway, this book. Okay, so we're doing this book. And you can follow along. I believe the contents of this book are free on the GitHub organization that uses it for course materials. So let me show that real quick, just to refresh you all. So it's IU compiler course on GitHub. The book is in this repository, Essentials of Compilation. And I believe they have, so they have releases, and you can just download the PDF and follow along if you want. And we're going to be doing based off of the Racket version, because that's the book that I have. They also have a Python version, but I'm not going to be covering that really. So, okay, so check out IU compiler course, and if you want to follow along in the book, go to this repo and download the PDF. Okay, so last time we got up to having a tiny language with variables, so let bindings in the Lisp parlance. And the next step is to try to generate x86 assembly language. So we're going to have a look at what we've done in the code so far. I want to review that. Earlier I was just making sure the tests still run. So this is our LVAR, so our language with variables, and it has very simple expressions. These are all abstract syntax tree nodes in here. So we have a program whose body is a single expression. And then an expression can be a literal integer. It can be a primitive operation. It could be a variable, or it can be a let binding. Which says here, bind this variable to this expression and then evaluate this expression with that variable bound. So you can imagine that if you build these let things, then you say, hey, define x to be this, and the value of this expression, and then down in this tail expression, you can use x using this var element. So this var expression. Pretty typical stuff in a functional language. So what we're going to do now is we're going to look at what we need to do to get ready to do x86 assembly, which is the next section. So if you're following along the book, I'm at 2.2, the x86 int assembly language. Okay, so they're looking at they give an example of the concrete syntax of x86 and like what a x86 program might look like in assembly. And I'll just type this out for you so we can get a sense, and I'll go ahead and make a int Gleam. Oops. I've got the fan on because it's warm in here today, but it makes the pages turn when I have the book set down. Oops. Rename. Let's remove the trailing thing. Okay, so what they're doing is how do I write comments? Okay, so their x86 program that they give as an example. I'm just going to type it in here, even though it's going to be invalid syntax. So they put global main, and they say main, and then it's like move q 10% rax, and then it's add q 32% rax, and then ret q. So this, let me go ahead and comment this out because it's not valid Gleam syntax. This puts 10 into the A register, the accumulator, and then adds 32 to it and returns. So at the end of this sequence of instructions, 42 will be in the RAX register. So that's essentially equivalent to the expression in Racket or other Lisps of plus 10, 32. Okay? So this is the sort of thing we want to generate today. Okay, and then as far as the the concrete, so this is the concrete syntax. The abstract syntax is going to be pretty simple because we're not including all of the instructions that are in x86 assembly. So let's start to spec out the concrete syntax. The book will stay. I need a better solution for this. Okay, I'm going to set it down. And I'm sorry that I keep turning my head down. I am looking at the book as it's on my desk here. Okay, so similar to what we did for LVAR, we're going to need to make some types. So register is going to be RSP. I'm going to name them like this, RBP, and we're just going to define all of the constructors here. RBX, RCX, RDX, RSI. Oh, whoa, don't complete that for me. RDI, R8, R9, R10, R11. So these are just the registers in x86 64 architecture. R13, the general purpose ones, as they say. Okay. 15. Okay. And then there's the idea of we need to think about what is an argument to one of these instructions. So we have several. And I want to, yeah, arg is fine. That's what they're using here. They use reg. I typed register. Maybe we'll shorten that to reg. So an argument can be either immediate and that's going to be an integer. So that would be like this. This $10 is an immediate value. That'll be part of the binary that's produced. That is not, it doesn't rely on memory at all. That's just in the source code. Okay, or it could be a register, in which case, so we need, that's a little bit confusing. Maybe rename this to register. Okay, you don't want to register. The bit here where it's like this, you know, needs to be named differently. I kind of, this is a thing they can kind of get away with in Racket, is that, you know, these can just be straight symbols, like literal symbols. But Gleam doesn't have that sort of thing. Now, like, we could say, oh, let's do this in Erlang, and yeah, we would have atoms. We could just use atoms for that and make an abstract type, or not an abstract type, but like a dialyzer type that is just the union of all of those atoms. But we don't have that in Gleam, so we have to reify that type. Or it's, so the third bit is a deref, which is a register and an offset, which is an int. So it's like, take the address in say this register and add or subtract something to it and get me the value at that memory location. So it's like treating that register as a pointer. Okay. So those are the three types of arguments. And then for the instructions, we have, okay, so they're defining instruction as similar to what we did over here in lint, except we didn't do it like they did. They were like prim, and then there's an operation name and then set of arguments, but we actually had to define this. So I think that we will go ahead and define all of these directly here. So we have add q, which takes an arg and an arg. And we have sub q, so subtract. And we have neg q, which takes an argument, single argument. We have move q, which takes an argument and another argument. One thing that this is not specifying is that I think there are certain kinds of arguments, especially on the right-hand side, which are not allowed. So, like on add and sub, I think that the b arg has to be a register. We might have to make some validations for that, because I don't know how to put that restriction into the type system here. We'll see. Okay, and push q pushes something onto the stack, and pop q moves it off the stack. Call q. Okay, so label is just going to be a string. And why does that take an int? Interesting. I don't know what that is actually. Anybody know x86 assembly and what that int is? I mean, I'll just call it int for now. I don't really like that, but maybe that has to do with number of arguments or something. Okay, and there's retq, which is just return, and there's jump, which takes a string. Okay, so now we have all the instructions. Then next there's block, and I'm just going to say body is list instruction. Is that how you do it? Yeah, okay. Right, okay. We're not, I don't know why that was imported. Okay, so then we've got a, then we have a x86 program. And that's going to take, we're going to ignore the info that they're putting on everything. I think that like we might have to go back and add those later, as they're probably using that for keeping intermediate state around, labeling things, so forth, annotations on the syntax tree. But this is just a list of pairs. So let's look at the in the book they're like it's label.block as lists. So let's look at the standard lib. And I think dict would be fine. Yeah, I think what we want there is yeah, so let's import Gleam dict. And this will be body is dict of string, which is a label, to block. Dict, there we go. Okay, so this is the abstract syntax of our x86 integer little language. Okay, I'm going to rewind to the beginning of this section and skim the prose and see what we need to do next. Okay, so program begins with a main label followed by a sequence of instructions. Okay, so there's a bit here where we should maybe have something that says you must have a main label. Maybe we can when we're generating this language, we can have some validations over the tree that is generated. Okay. Yeah, for our purposes, a computer's memory is a mapping of 64-bit addresses to 64-bit values. Computer has a program counter stored in the RIP register, RIP, which is not an argument here. Like honestly, you tend to not use that register directly, except to maybe read it. Jump instructions, branch instructions, and so forth. Call, return, those update the RIP. Okay. For most instructions, program counter is incremented after the instruction is executed, so it points to the next instruction in memory. It's fine. Okay, immediate values registered memory locations are the arguments. Okay, register is special kind of variable. Right, immediate value is written with $. Access to memory is written as n% and with parens %r, which obtains the address stored in registry R and then adds n bytes to the address. Okay, so that would be like if we had here, if we did like that, that would say take the address in here and then add 8 to it, and that's your argument. So this would move 10 into the position 8 bytes past what RAX points to. That's what we're doing. Okay, so the right, so in these instructions like add q, sub q, neg q, for example, they always take the rightmost. I mentioned this earlier. They take the rightmost argument as the destination. move queue as well. So this is saying move this into this location. So again, a literal is not, like an immediate value is not valid in that right-hand position. It would have to be a register or a deref for the right. I don't know about add queue and sub queue. I'm assuming that those have to be registers. Okay. Let's see. Okay, so there is an appendix that is a quick reference for all the x86 instructions. Okay, so they're saying by convention and the value stored in RAX at the end of the program is the exit code, which you may be aware of if you use like C or anything else that compiles to machine code, that like you can return an integer from your main function, or use an exception type and have the runtime or the compiler of your language will set that exit code for you. Sometimes you can explicitly call exit with an argument which is non-zero to terminate early. Basically, they're saying here that the convention is that you return 0 if it's successful, but in this book they're returning the result of the program as the exit code. So if you want to know what the result of computing this program is, that's the exit code. I don't know how I feel about that. That's kind of weird. I understand for the purposes of instruction, that's fine, but it might just make things confusing for people later. Okay, we exhibit the use of memory for storing intermediate results in the next example. So 2.8, yeah, let's type out that so you can see it. It computes let's just get typing. So it computes this expression plus 52 negative 10. Okay. This program uses a region of memory called the procedure call stack, or the stack. The stack consists of a separate frame for each procedure call. The memory layout for an individual frame is shown 2.9. Oops. Right, okay. The register RSP is called the stack pointer and contains the address of the item at the top of the stack. Okay, so they say pointers for something that has an address in it. So we were talking about earlier about indexing on top of this register. Then you that would go like add or subtract that from that address, and then referring to that address would use that as the argument, the value at that address as the argument. Okay. Okay, so that's what they say a pointer is. The stack grows downward in memory, so we increase the size of the stack by subtracting from the stack pointer. This is a thing with x86 architecture, and I think it might even be a convention in a lot of operating systems, regardless of the architecture. But the heap grows up from the bottom, the stack grows down from the end of the memory space. Okay. So it's a little bit, you think like, oh, the top of the stack, actually the top is lower memory address than the bottom of the stack is. But like conceptually our brain is like, oh, you put it on top, so it has like a higher address. No, it has a lower address. Okay. So in the context of a procedure call, the return address is the location of the instruction that immediately follows the call instruction on the caller side. Okay, so the function call instruction, call queue, which we have defined in our type here, pushes the return address onto the stack prior jumping the procedure. The register RBP is the base pointer is used to access variables that are stored in the frame of the current procedure call. So if you can think of the stack, they have an example. So they have a table, and I can't read it and show it to you at the same time. But they're talking about the frame, the memory layout of a frame. So the return address is, one word behind the base. Okay, we're gonna have to get some more context on this. So the base. So if you think of the, RBP, it's like the lower bound, or it's actually the upper bound if we're talking memory addresses, but it's the lower bound of variables in scope. And then RSP is the upper bound of variables in scope. So when we are doing call queue, we push the return address on the stack, and then we put the old base pointer. So we had, so this is RBP 0 and RSP 0. If we want to do a call, then we do basically move queue, or no, we push RBP. I'm sorry. No, we push the return address. So we push RIP, I guess. And then we push Q RBP. This is probably not correct. This is like, we would want a label or something. We'll just call it ret label. Whatever that is. I don't know. This is not correct syntax, by the way. I'm just trying to figure out the calling convention. So then we would push RBP, so it goes on top of the stack. And then we do call queue. So that the top portions of the frame are where RBP was before, and then what the return address is. This is what's called a calling convention in this level. So this is, I think, roughly the C calling convention. But regardless, like the RBP and the RSP are the bounds of the stack that you use in the current function. Okay, we're going to get back to this. So to look at their example that they're building here, so they have a start label, which is move Q $10, and so they're putting 10 into the slot just above the base pointer on the stack. Note they're not pushing, which is interesting. So they do neg q. Okay, so this does not need to be a register, I guess. %RBP. So now they're negating it, negating 10. Okay. And then the next step is they do move q. So they're moving that bit, I'm sorry, that value into RAX, because RAX is going to be the destination register for the return value. And then they add Q 52 to RAX. And then their jump conclusion, which we'll find out what that means. Okay, so then the main, which again has global main, global without an A, makes sense. Main has push Q RBP. So this is what we were talking about just a minute ago with the calling convention. So push Q RBP, and then we move Q RSP to RBP. So this is saying we push the base pointer onto the stack, so that goes onto the frame that we were talking about before. And then we're putting the top of the stack into RBP. So this becomes, the top of the stack becomes the new base of the next function that's going to be called. And then it says sub Q 16 RSP. Why would we do that? Oh, so this is making space for the variables. Let's see, 16 bytes would be 64, right? So this is saying put the stack pointer. You've stored the old stack pointer in RBP. Put the stack pointer one word above where it was. So that's the top of the stack for the next function. And then it jumps to start. Okay, so this is not using call queue and ret queue, by the way. Okay, so the conclusion label has add queue 16 RSP. So this is the thing that's brain bending about this, is you're manually, it's not like the stack is not a data structure. You're implementing the internals of the stack data structure on top of CPU registers. So this is moving. So this is where we jump from. This is putting the stack pointer back down a word. Okay, and then it does pop Q RBP. So previously this is, so we're undoing the add 16 or the subtract 16 with the add, and then we're taking our basically what RSP points to and putting it back into RBP. So we had previously pushed it, and now we're popping it, okay, into RBP. And then the final thing is ret queue. So that's sort of their overview, what this would look like in assembly language. Very much not optimized, obviously, but pretty straightforward while still demonstrating what the calling convention looks like. Okay. Sorry about that little digression. I think that's important for me to understand, and hopefully for you all. Okay, and now they're going about explaining it. Yeah, so the first three instructions under the label conclusion are the typical conclusion of a procedure. First two, restore RSP and RBP to the states at the beginning of the procedure. So when this came in, or before you jumped into it, what were the states of those two registers? It says, in particular, add Q16 RSP, this first one, moves the stack pointer to point to the old base pointer. So that's like adjusting it so that it is at the previous location. And then popq RBP restores the old base pointer to RBP and adds 8 to the stack. So that's taking RBP off the stack and restoring it. Okay, and then retq jumps back to the procedure that called this one and adds state 8 to the stack pointer. So there's retq will take off the stack the address that was before you pushed RBP. Okay. Okay, now we're done with the description of this particular syntax. They say our compiler needs convenient representation for manipulating x86 programs, so we define abstract syntax, which is what we did here. We implemented their abstract syntax as data types. The main difference between this and the concrete syntax of x86 is that labels are not allowed in front of every instruction. Instead, instructions are grouped into basic blocks with a label associated with every basic block, which is why the x86 program struct contains an association list mapping labels to basic blocks. Okay, so eventually we'll need that info structure. The same thing happened on the original language. We just removed it. We just left it out. Okay. Right, okay, so this is the arity of the function. So this is a bit I missed earlier, which basically means that for the sake of making a call, this is about how much we need to push onto the stack before we jump, right? The number of arguments. Okay, that's helpful to know during register allocation. Oh, okay. So when we get to chapter 3, which is like register allocation is one of those things that I've always felt is really magical, but we'll learn about probably next time, because this particular chapter, I was hopeful that we would finish it and go directly into chapter 3. Maybe we'll start reading some of chapter 3 today, but I want to get us to actually generating this this assembly language code. Okay. Okay, so now I'm at section 2.3. We're done talking about the abstract and the concrete syntax here, and what they're talking about is the section is titled "Planning the Trip to x86." So they say to compile one language to another, it helps to focus on the differences between the two languages, because the compiler will need to bridge those differences. Yes, absolutely. This Lisp-like language in LVAR has many differences from this very imperative language in x86. So arithmetic instructions typically have 2 arguments and update the second argument in place. This is in contrast to LVAR, arithmetic operations, which take 2 arguments and produce a new value. So we'll need to be able to bridge that gap. And then an x86 instruction may have at most 1 memory accessing argument. So that was like deref a register something, right? Furthermore, some x86 instructions place special restrictions on their arguments, which we may have already alluded to. I'm not sure what the restrictions are yet, but we'll find out. Okay, an argument of an LVAR operator can be a deeply nested expression, which we saw over here, like, plus can have 2 expressions, and that expression, it's self-recursive type, so, or at least mutually recursive. That could be, another primary or primitive operation, which goes back, and this has more nested expressions and so forth. That doesn't exist in x86. x86 instructions restrict their arguments to be integer constants, registers, and memory locations. Yeah, go ahead and save this. Okay, the order of execution in x86 is explicit in the syntax, obviously, which is a sequence of expressions and a sequence of instructions and jumps to labeled positions, whereas LVAR, the order of evaluation is left to right, depth first traversal of the abstract syntax tree, which we saw when we did this, interpreter, right? So the interpreter walks the tree of expressions, and left to right, depth first is the basic type of interpreter. Okay. A program in LVAR can have any number of variables, whereas x86 has 16 registers and the procedure call stack. So there's even a different way of deciding where some intermediate value will go. Then here it's like, well, if it's a variable, we create a let binding, we stuff the thing in the let binding, we refer to it later with var or whatever. Okay, variables in LVAR can shadow other variables with the same name. In x86, registers have unique names and memory locations have unique addresses. So if we want to shadow a variable in x86, it's basically saying we need it on the stack, right? So if we use it in a procedure, in an expression that is deeply nested, then we need to have that address of that variable higher up in the stack somewhere. Or maybe it needs to be something that is pushed onto the stack when we call the procedure. Okay, so they say we ease the challenge of compiling LVAR into x86 by breaking the problem down into several steps, which deal with these differences one at a time. Each of these steps is called a pass of the compiler. This term indicates that each step passes over or traverses the AST of the program. Furthermore, we follow the nanopass approach, which means we strive for each pass to accomplish one clear objective rather than 2 or 3 at the same time. We begin by sketching how we might implement each pass and give each pass a name. We then figure out an ordering of the passes and the input-output language for each pass. The very first pass has LVAR as its input language, and the last pass has x86 int as its output language. So there's going to be a bunch of steps between these two things. In between these two passes, we can choose whichever language is most convenient for expressing the output of each pass, whether it be LVAR, x86 int, or a new intermediate language. And this is like the essence of the approach of this book, is that you make lots of tiny little languages that you translate one tiny step at a time. And that makes the goal of that is making each step really comprehensible, and not too large in scope. And I think that a lot of industry compilers do not follow this approach, and it makes, in some ways, it makes changing them hard. They probably will have better performance than this thing that we'll ever create, because they're able to combine steps to get efficiencies. But this way, this is about learning, right? What are the essences of a compiler? This is not about creating something production ready. And I don't ever expect this project to reach that point. I just want to get through as much of this book as we can on stream. Okay, so finally, to implement each pass, we write one recursive function per non-terminal in the grammar of the input language of the pass. That's not that surprising. That's pretty typical. Okay. So our compiler for LVAR consists of the following passes. And I don't know where this is going to go. Let's just outline it in here. So there's uniquify. Great name, right? If I can spell it. So that deals with shadowing of variables. By renaming every variable to unique names. So this is like static single assignment is what this is called, by making unique names. Static single assignment is the other word for that. Okay. Remove complex operands. Ensures that each sub-expression of a primitive operation or function call is a variable or integer. That is an atomic expression. Okay, so right, we refer to non-atomic expressions as complex. This pass introduces temporary variables to hold the results of complex sub-expressions. Okay, so this is ensures atomic operands of primitive ops. So an example of what that might do, so if you had an expression that was like what we saw earlier, neg10, the transformation should look like let a say let a10, and then we're going to there'd be another let binding, which would be let b, how would we do that? It might be like negative a, and then inside there we would do plus 52b, something like that. So the idea is introducing intermediate variable bindings, so that all of your arguments are, and actually we probably wouldn't need this let a, it would just be let b -10, because that neg expression is already atomic. That is a literal. So it's kind of unwinding things, and you can see there that this will lend itself to generating that that'll lend itself to generating the code for the x86 expressions, because you can see here that like B could become a stack location or a register, probably a register, we don't know for certain, and then potentially, you know, you would move B into a register, and then you would add 52. So you can see how like this becomes closer to the x86 representation. So denesting things, turning them into temporary variables that get pushed into expressions further down. Okay. Oh, wow, what a name. Explicate control. So it makes the execution order of the program explicit. Okay. So this is probably related to the complex operands. Explicit execution order. Yeah. So it converts the abstract syntax tree representation into a graph in which each node is a labeled sequence of statements and the edges are goto. So there's going to be some kind of goto-like language. Okay. Or some other language that has that kind of graph with gotos. Some other language that has something like a goto in it will be the intermediate language there. Okay, then select instructions. Handles the difference between LVAR operations and x86 instructions. So this pass converts each LVAR operation to a short sequence of instructions. Okay, convert LVAR into instructions. Into sequences. So you could kind of, I'm guessing that you can kind of think of it like, you know, we had our example of plus 52 neg 10. you might take this inner expression, and there might be a template for this, which is like move q whatever the input is into rex, and then neg q rex. So it's kind of like having templates that you could fill in, and in this case we'd fill it in with $10, right? So that's kind of what that, I'm guessing that pass is like. And then finally, assign homes. So and this is replaces variables with registers or stack locations. Okay. Yeah, so they say that remove complex operands and explicate controls are a quintessential example of this nanopass approach. You could understand how these would be really tempting to group together, but they do not group them together. Okay, next question is, what order should we apply these passes? This question can be challenging as it's difficult to know ahead of time which orderings will be better. That is, will be easier to implement, produce more efficient code, so forth. For ordering, often involves trial and error. Nevertheless, we can plan ahead and make educated choices regarding the ordering. What should be the ordering of explicate control with respect to uniquify? The uniquify pass should come first because explicate control changes all the let-bound variables to become local variables whose scope is the entire program, which would confuse variables with the same name. So doing the static single assignment is important first. We place remove complex operands before explicate control because the latter removes the let form. So explicate control would get rid of let bindings. But it's convenient to use let. It is convenient to use let in the output of remove complex operands, right? Because we're talking about taking those expressions that are deeply nested and flattening them. Well, they're not really flattening them. You're like extracting the inner parts into let bindings, right? The ordering of uniquify with respect to remove complex operands does not matter, so we arbitrarily choose uniquify to come first. Okay. Okay, the select instructions and assign homes passes are intertwined. Okay, in chapter 7, we learned that x86 registers are used for passing arguments to functions, and that it is preferable to assign parameters to their corresponding registers. This suggests that it would be better to start with the select instructions pass, which generates the instructions for argument passing, before performing register allocation. On the other hand, by selecting instructions first, we may run into a dead end in assign homes. Recall that only one argument of an x86 instruction may be a memory access, but assign homes might be forced to assign both arguments to memory locations. So a sophisticated approach is to repeat the two passes until a solution is found. So like compute a fixed point, right? However, to reduce implementation complexity, we recommend placing select instructions first, followed by the assign homes, and then a third pass named patch instructions. So we're going to have patch instructions, which they don't say in their original thing, that is used as a reserved register, or that uses a reserved register to fix outstanding problems. Okay. So looking at their diagram, so let's talk about what this does in terms of transformations. So uniquify is going to start with LVAR, because that's our input language, and it's going to produce LVAR. They're not introducing any new abstractions here. We're just renaming let bindings, right? Okay. So then there's remove complex operands. And they say that takes LVAR and produces LVARMON, I don't know, or LMONVAR. They've got these like mathematical looking symbols for these. So what's the difference here? Okay, so I'm sorry, there's one more. What do they say? Patch instructions. Fix outstanding problems is what they say. Okay. I don't know if LVARMON or LMONVAR is even a separate language, or if it's just that they've made all the operands atomic. It's not clear. Okay, so then explicate controls next, and they say that goes from LMONVAR to CVAR. Okay, we'll learn what CVAR is. Let's finish this out based on what they say. Select instructions goes from CVAR to x86 var. Okay, which I'm guessing is going to be an x86 with variables, which will get assigned locations in the assign homes pass. So this is going to take x86 var. Yep. Oh no. Assign homes. Okay. x86 var to x86 var. I can't type. The patch instructions phase goes from x86 to x86 int. So this is the thing that we made already. So we've got a lot of steps to fill in here. And then there's a prelude and conclusion. Excuse me. So I'm guessing that this is like, you know, puts the boilerplate around our program. And that goes x86 int to x86 int. Okay, so the last pass, prelude and conclusion, places the program instructions inside a main function with instructions for the prelude and conclusion. In the next section, we'll discuss the CVAR intermediate language. So we're going to have to make a new one. Let's make a new file, CVAR. Okay. We're at section 2.3.1, if you're following along in the book. The output of explicate control is similar to the C language in that it has separate syntactic categories for expressions and statements. And like this is the essence of this translation, is we've got to get something that is fully expressions into fully statements, right? So so this intermediate language bridges that gap, is what they're saying. The style of the intermediate language is also known as three address code, to emphasize as a typical form of statements such as x equals y plus z. So three addresses, x, y, and z. The concrete syntax, we don't actually care about concrete syntax, do we? Maybe we do a little bit. But let's go ahead and make the abstract syntax. So, let's see. The CVAR language supports the same operators as LVAR, but the arguments of operators are restricted to atomic expressions. Okay, so that means that basically you can only have atomic expressions. We've already done that pass. So there's no when you get to this intermediate language, there's no complex operands. There can only be atomic expressions. Okay, instead of let expressions, CVAR has assignment statements that can be executed in sequence using the SEQ form. Okay, a sequence of statements always ends with return. A guarantee that is baked in the grammar rules for tails. So we'll see that in a second when we build out the syntax tree. The naming of this nom-terminal comes from the term tail position. So like tail recursion in languages like Gleam, but tail position, which refers to an expression that is the last one to execute within a function or program. Okay, and then a CVAR program consists of an association list mapping labels to tails. Okay, that makes sense. This is more general than necessary for the present chapter, as we do not introduce goto for jumping to labels, but it saves us from having to change the syntax in chapter 4. Okay. For now, there's just one label start, and the whole program is its tail. Yeah. Okay. So the info field of the C program form, which after the explicate control pass, contains an association list that associates the symbol locals with a list of all the variables used in the program. Okay. All right, so let's get started on this. The abstract syntax. Okay, so I'm guessing this is this can be an int, which is an int, or a var, which this is name. Okay, so this is pretty similar to what we've seen before, but this is an atomic expression. It's either a value or a variable in the CVAR language. Okay, so an expression can be an atomic, these probably need names. We'll do like that. It can be a primitive, and here they're doing the different. So we're going to need a prim op, right? Which is going to be read. You know, same type of operations. Negative, which is going to be arg is going to be an atomic. So note here we're not going to be able to nest prim ops, which is the big transformation that is done in a previous phase. Okay, and then plus is going to be A is going to be atomic and B is going to be atomic. So no nesting. Minus A is atomic and B is atomic. Okay, so we have a shoot. I love it when it does that. Okay, prim is going to be an op is a primitive operation. Okay, and then there's statements. The only statement that you have is assign. There's an interesting thing here where we're gonna have. I think we might need to do this. And the reason I'm thinking that is that what it wants here, because there's going to be assign has a variable and an expression. And while, you know, we could just use string here, sort of like what we did we do that over here? Yeah, we did let var string. We didn't make it a known type for var. Like it's just an expression with an a name as its contents. But I'm thinking we might want to be able to use this to pattern match against things that are in the rather than dropping down to the string that's inside it, if you follow. I don't really like this, but I think we need to go forward with it. Okay, and then here this is an expression. So the only statement is an assignment expression. And then there's a tail, which is either return of an expression, or it's a sequence of a statement and a tail. So you can see here that this is kind of like we're building a cons cell almost, where we're just going to have lots of nested sequences, and every statement is a sign. And then eventually, in order for this self recursion to finish, you need to have a return, which is a simple expression. One of those things. Okay, and then finally the program. And this is going to have info, and we need to import dict here. So this is going to be, this is a label. So they said it was association list of label to list of var, and this is another reason why I wanted to make var its own type. Otherwise, it's list of string, which I guess is okay. I don't know yet. We'll maybe find out. Okay, and then they say you can make an interpreter for this. And they have that in the support code. But I think that's not the most interesting bit right now. I would like to go on to the next section, which is Uniquify. And hopefully we can get through that pass today. So let's make Uniquify. So its input has to be let's import lvar, right? So this is going to be, it's going to be an lvar program, and it's going to return an lvar program, right? Okay, so the Uniquify pass replaces the variable bound by each let with a unique name. Both the input and the output of the Uniquify pass is the lvar language. For example, the Uniquify pass should translate the program on the left into the program on the right. So let's write their example. So they have let x32 plus let x10 x. Okay, so what they're going to do is translate that into let x.1 32, let x.2 10, x.2, right there. Oh, wait. This needs to go outside that paren. I don't know why their syntax uses that extra paren, but Okay, x.2, x.1. And this transformation should be pretty straightforward. Okay, here's another example they give. Let, and this is x, and then have another let binding in the expression here, x4. This is gonna make me dizzy. Okay, so here they do plus x1. So that the result of this expression here gets bound to this x, and then after that binding they do plus x2, and they're saying that translates to let x.2 let, and this should reveal how we should do the recursive uniquifying. Okay, so that gets x.1 is 4 plus x.1 1. Yep. Okay, and then after that binding it's plus x.2 2. So you can see that this needs to be basically depth first from this example. Okay, we recommend implementing uniquify by creating a structurally recursive function called uniquify expression that does little other than copy an expression. However, when encountering a let, it should generate a unique name for the variable and associate the old name with the new name in an association list. The uniquify exp function needs to access this association list when it gets to a variable reference. So we'll add a parameter to uniquify expression for the A list. Okay, so we'll figure out, let's put to do in there. We'll figure out what this looks like, uniquify exp, and based on their thing, they have it be a lambda. I don't think that's necessary for our case. We can just directly call it. So this needs to be, this may be an issue where, we were thinking about having var be its own type. It might be useful. We're going to need our trusty dict again, because we don't have association lists in the okay. So they have a template for this particular operation, this function. So it takes when we say this lvar expression, and then it takes the env, which is a dict of honestly, since we don't have a separate var type here, it's just going to be string to string. And and that should return an expression, right? Okay. So essentially, Uniquify is going to call Uniquify expression of p dot, because this is a program, right? P dot body, and then it's going to return lvar dot program of the resulting expression. So we can probably inline that. Okay. What's wrong here? Oops, I have a typo. I can't figure out what to do with this. Okay. Yeah, this code is incomplete. Expected 2 arguments, got 1. So this is going to, it needs an env. So we'll have dict.new. Okay. So at the beginning of the program there, or the beginning of this evaluation, there's no bindings. So now we need to do, let's do case over the expression. We're going to add the missing patterns here. So in their template, so an integer just gets returned directly. That doesn't have to change. It's not, there's no variables involved in that expression. Okay, so I'm going to move this one up, do it in the order that they have in the book. So we have to figure out what this is, right? And we also have to, for variable expression body, we have to figure out what that is. And then for a primary, and this is why I think they and I need to get it to fill out. Help me, buddies. I don't want to fix with assistant. Can you give me the other? Oh, I need lvar dot plus add missing patterns. So they do, this is why they do the named operation plus list of arguments. But we have to expand that because of how we design that. Okay. So in this case, there's no variables in this expression, so we can pass that through directly. Negate is an expression, so we need to uniquify expression on V. env. Right, and then we rewrap it. Okay. Let's look at minus. this is going to be similar. So we'll do lvar prim, lvar minus, and we'll do uniqueify. This is looking really similar to the stuff that we did on the interpreter, right? This is the same sort of traversal of expressions. So again, the reason why these primitive operations operate like this is that, or that we're writing it like this, is they don't introduce any new variable bindings. So really, I'll change this one to plus. So those are really straightforward to do. What are we missing? What did I do wrong? Too many parens? Not enough parens. Okay. So it really comes down to what do we do in the var and the let cases? These other things are like really straightforward. So for the var case, what we need to do is look at how this original, remember this example, so like here x is 32. When we get inside this expression, what is this x bound to? Or what is it, how has it been renamed? It's been renamed to x.1. So when we introduce a let binding, we need to inject a new unique name for that variable name. So this var v is a string, right? Okay. So what we can do here is we can rename this variable and we need some kind of, like, I think we did this in some other language. We have some panic where if it's not present, not in that one, be an lvar in our interpreter. Yeah, we have get var. So I think that we need to make use of this. And maybe we can make it generic rather than just over this. Because this is for, why don't we just copy this and put it over here? And this will be addictive string to A. And this will return A. Okay, and then it's just saying it's never used. Yeah, so we want to, in our case it's a string, but so we'll do get var here of env v, right? Okay, so we should never have a case where we introduce a let binding that doesn't have a mapping in this env, which is what we need to do in this clause. So we're creating a variable and we're binding the value of that variable to this expression and then using that variable in the body. So what we want this to look like is there's an lvar.let. How do we do something similar over here? Right. Okay. So we're gonna create brackets here. So we're gonna make a new name, and we might need to make use of something from the standard library for this. So let's have a look. We can append strings. I think we can do that with the angle brackets. Um, I don't know that we want random. What might be interesting is to have a state. Yeah. Because note that they, in their examples here, they're like, add a subscript. So let's see what we can do here. So if there's a variable, so if there is not a variable, actually we don't care. Let's see. Let's look at dictionary. Okay, so we don't care about the error case. So what we'll do in this case is we'll say v and add .1. Okay, and if there is one, then what we'll want to do is see if we can parse. This feels like maybe over-engineering it. But I would want to do... Okay. We're going to have another case. So let's import Gleam string. Okay. We're going to use split once on dot, and that should split into two substrings. Okay. And then if we what I would really love to have instead, but I'm not doing it here, is just have a counter that we increment. Actually, let's do that. Let me back this out for a minute. That was getting to be a bit too much. And let's take a counter, which is an int, and then we'll pass 0 at the beginning. So so here we need to pass in counter. If the problem is that's not going to make it unique. So like if we get two branches here and they both have the same variable in the let binding, they're both going to get the same count. So honestly, I think the other option is that this returns uniqueify expression, returns expression, but also the counter. that will let us track it through these. I don't know how I feel about that, but let's try it. Okay, and then we'll do let. Okay, so this case, you know, doesn't change the counter. Neither does this case. Oops. Counter. We'll deal with let in a minute. But we need to turn this into gonna mess this up. Eventually we'll do this. So this is A1. And we'll thread this counter incrementer through. So we'll do here B1 counter 2 is uniquify expression B, E, and V, right? So forth. Counter 2 or counter 1. And then we'll return this B1 and counter 2. And we need to do this for all of the things below. Okay, why don't I just do like so, and this is minus. Okay, and then here, like this is a case where, oh, if we were using some language that is not immutable, we would not have this problem. But you know, you have to if you want to thread that state through, you need to track it explicitly. Okay, so read does not change the counter. These will potentially update the counter by unifying those internal expressions. So now we don't need to know what the previous one is. We just have the counter, right? So what we're going to do is we're going to make a new name, and that's going to be the variable name plus dot plus int to string of, say, let new counter equals counter plus 1. So we know we're going to increment it. We say new counter here, and then now that we've bound it, no, that's wrong. We want to recurse into this expression first, because remember, in their example up here, this one gets the lower one, so we need to recurse into the expression. So we're going to say E1 counter 1 is uniquify expression of, that takes E, and it takes E and V, and it takes counter. Okay. And then we're going to create a new name. We'll call it V1 is going to be V plus dot plus int toString of counter 1 plus 1. So we created a new binding. We don't know what happened down in there, but now we're going to do let's body 1 counter 2, right? We're going to uniqueify expression of body, and then we're going to insert V refers to V1 in this scope, right? So this is the binding that we're created. This is the name, but when we go to look it up, we want to make sure that the name inside this scope is replaced by this new name that we created. Okay, and then counter 1 plus 1. I kind of don't like doing this. Let's say let counter V is this, and not the greatest code here. Okay, and then what we return is our let again. So we've restructured the let, so it's binding to V1, expression 1, body 1, and we're returning counter 2. Okay. Oh, we need to do insert into env. Okay. I think this is it. Let me know if you're following along, all right? So let's look at their example here. Okay. Let's construct one of their examples and then see what our thing does. And maybe we should just do this as a test, right? So over here in compiler test, we'll probably have to export this, right? Yeah, hopefully we'll get done with this uniqueify by the end. So what example? Okay, so uniqueify test. Okay, so let's make a program. Compiler uniqueify. Okay, and we're going to import lvar program let. We're going to need plus negate we just need plus for our first example. So let's leave negate off. Int. Right? And var? Yeah. Okay, I'm going to copy this example over. And we'll see if we did this right. So this is the example that we're going to construct. So let's make P is a program. And that's going to have an expression in it, which is let and that's going to take x and an expression is int 32, and then inside that it's going to be plus, right, because let takes an expression. Okay, plus, and the left side of that is going to, okay, so the right side is going to be var x, right? The left side of this plus is going to be let, and here it's going to take x and bind it to int 10, and then the expression is just var x. Okay, we need a prim. And okay, let's unqualify that. Okay, so that's our program, and what we want our output program to look like is this same form, but it's going to be the inner, let's see, what do we do? Oh yeah, so the first one is x.1, and this is going to be x.2, and this is x.2, and this is x.1. And let's see if we got our algorithm right here. So let me look at our test. Okay, so we're going to say p uniqueify should dot equal p1. All right, let's run that test. Okay, wow, it passed. First attempt. Okay, so we're not using that, so we can remove it. Cool. Let's build this one. Okay, where's our test? So let's just make a new one. Uniqueify inner let test. Okay, so this is the thing we're trying to reproduce. I think we can copy a lot of this and modify. So so this is going to be, we have a program again, and we need to, that has a let in it with x, and then the expression in here is another let, which has x and int 4. And then the expression there is a primitive operation of plus var x and int 1. Okay, so I need to put some breaks in here so we can read this. This is a challenge with these sorts of things, is you make them really nested. And without without editor support, like there's ParEdit and Emacs, which is really great at dealing with Lisps. Helps you out a lot. It can also be a pain if you're not used to it, but it can be really helpful. Okay, so now we're on the right-hand side of the outer let, and we have another prim, which takes plus, and this takes var x and int 2. Okay, and that's syntactically correct, so let's copy that and go rename the variables, and then we'll have our test. Okay, so this one becomes x2, This inner one becomes x1, and this is x1, and this is x2 on the outside. Okay, wasn't so bad. And our test still works. So the I don't know that it really matters that much that these examples exactly work the way that they show in the book, but it does impress to me that we did the right thing in this algorithm. So let's take a look at it one more time. Right, so we're starting off with there's the goal of the uniquify is to make all let binding variables globally unique. And every pass will either, like, so for variables, it's just find the alias for this variable that is in this scope, and don't modify the counter. For integers, there's, it's a literal, so there's no variable binding, so the counter doesn't increase. We'll go back to the let. For each of the primitive operations, we are recursing into uniquifying their sub-expressions and incrementing the counter where necessary, where lets exist inside those, and then passing along the counter. And then, obviously read doesn't have any sub-expressions, so it doesn't modify the counter. And then finally, in the let, we uniquify the expression that is going to be bound to the variable. We increment the counter and then rename the variable with that subscript. And then we uniquify the body using the alias. So if it encounters this variable, which it should if it's useful at all, if it encounters this variable and it's not dead, then it'll hit this expression at some point and pull that new alias out and replace it. So that's pretty cool. There's our first one. I'm tempted to potentially move this to its own module. Let's see about that. Because there's not really a reason to have this in here other than that's where I started typing the notes. Let's make a new file called uniquify. Why is that so hard to type? Okay, and we're going to move all of this in there. Okay. And then here we're going to, let's make a new file, uniquify test.gleam. And we'll move, I think I want to keep this top level compiler test for the, let's copy that and modify. I want to keep it for like integration level tests or something. So we're going to say uniquify. And then the compiler, we can get rid of a lot of this. Doesn't need that, doesn't need those things. And what does this need? This needs import lvar. Import gleam dict. Import gleam int. Do we need anything else? Okay. Oh, whoops, I removed those. Yeah, we need to leave those in there for now. Okay, these are not included. These are not included. These are not used. I don't know if every module has to have a main in it. Still has 4 tests, which there's 2 in here, and there's 1 in each of these. So I don't know that you need a main in every test module. You just need it in the main one, or it's somewhere in one of them. Let's see if there's still 4 tests. Yep. Okay, cool. I wonder if I even remove it from here, if it still works. No, okay. So you need it somewhere. Okay. This is probably a good place to call it for today. And then what we'll do is we'll come back next time and we'll make these other passes. So maybe it would make sense to, before we close it out for today, organize this a little bit differently. Let's make a new folder here called passes. And let's make another new folder here called, we'll call it langs. And then let's move let's make langs passes. Okay. Move that in there. And we'll move these into langs. Okay, and before I move anything over here, let me make sure that that still runs. Okay. Yeah, it still finds everything down there. Because what I want is, like, these files should be as standalone as possible. So let's see about moving that. We're gonna have to do a bunch of renames. And I don't think that the language server is going to help us with those. So I'm gonna try to make it as quick as possible. So let's move these into langs. And let's move uniquify into passes and langs x86. Okay, so this needs to be langs. And then we're not importing anything special in this one. We're not importing anything special in this one. Right. Yep. Okay. And so the issue here is we need langs lvar. And I think then we just need to update the tests. And uniquify test needs to be passes and langs. All right, let's see if we've got any problems. The LSP seems to think we're fine. Let's run the tests. Okay, that I think will set us up for for this working better in the future, because there's going to be a lot more passes as we go forward. Source and test. Okay, and so it's just showing we renamed. Yep. Okay, this is chapter 2. This is we have defined cvar and x86 int and created first transformation uniquify. All right, pushed everything up. Thank you for attending today, if you're still here, and we will see you next week. We'll continue through. Hopefully we can get through more than just one pass. These things are not necessarily straightforward. I have to use my brain a lot while I'm talking, but we'll catch up again next week and keep going on generating assembly language. Thank you for coming, and